Let's start our second talk. The speaker is Xiaoming Yuan from the University of Hong Kong, and his title is How Optimization Helps Industry. Some real applications in the era of AI and cloud computing. Let's welcome.
Thank you. Yeah, thank you for coming to my talk. And this is a rescheduled talk. I was supposed to give talk in the afternoon of Wednesday, but all of a sudden I got the notification that my talk was rescheduled today. And usually I get up very late, but today I get up very early to catch up the talk. Anyway, so today what I'm going to say is some real applications. We are all talking about applications of math. This is DIMSA. This is for Application Institute. And then, that's why I want to present some real applications for you in the era of AI and cloud computing. And in particular, I'm going to focus on how optimization can help solve this kind of problems. Optimization itself cannot solve any problem in industry, but optimization can help solve this kind of problems along with some other technologies. Yeah. So very quick background, just in case you have no idea about what is cloud computing, but I'm sure you are using cloud computing every day. So formally speaking, cloud computing just provides the computing services on the internet, including the server storage and the databases and the networking of software and the intelligence. So we just put everything in the cloud, in the center. So the center will help you solve the computation, compute for you, and then just deliver the result to you through the internet. So formally speaking, cloud computing is the ICT, Internet Communication Technology industry. Okay? And formally speaking, I started to work with some industry for cloud computing 5 years ago. And I got an offer from industry, and then we started to work together, although I didn't accept the offer as a full-time staff in the industry. And then, of course, we have a lot of motivations to do the cloud computing because the data processing and the storage can be more effectively performed in large pools of computing, and the storage resources are accessible via the internet. So this is what we call the benefits of the scale. Sometimes, it can be more economic if you put more things together. So this is the benefits of the scale. And there are some major providers in the market for the cloud computing, like we have AWS, Google, and Alibaba, Tencent, and Huawei for the domestic markets. And cloud computing is fundamental, to economic infrastructure. So it reflects the national scientific and technological levels and the core competitiveness. So all the major countries actually now are putting their resources in developing the cloud computing. So this is a key infrastructure for economics. So some very simple applications, social media, we're using it every day. The video and the music, for example, streaming services, we're watching the video every day, TikTok and WeChat. Okay? And some healthy wearable devices. Okay. And this to give you some idea about the market. I use this kind of slides for some MBA students. Okay. Once I was invited to give a lecture to MBA students, so I showed this to the MBA student to see how important the cloud computing market it is, right? So you see, actually, the cloud computing market size is going to increase, okay, from about 3 years ago to 7 years to 6 years later. You will see, actually, the size will be increased by how many times? I think by 5 times more. So in a few years, in 10 years, so the market is huge. So mathematicians should not be left behind of the big, economic developments. We have to be a player in the markets. In particular, the applied mathematicians should be involved in this market, very huge market. So you see, so what is the optimization in cloud computing? You see, as I said, basically the cloud computing means we have got the resource in the cloud, and then individuals have different applications. So the cloud is controlled by the so-called controller. So the controller of the cloud actually have to make decisions. Okay, we call it actuator. Okay. So there are a lot of challenges in the resource management of the cloud. Okay, so if we want to be a player in managing the resource in cloud, then we have to solve so many different resources questions. So first of all, for example, we have to manage the vast and the complex infrastructure, and we have to coordinate the interconnected services and resources, so on and so forth. So there's so many different types of decisions to make if you want to control the cloud. Okay, so the role of optimization is very crucial for modeling the tasks in cloud resource management. So we use different optimization and operational research resources, technologies, to try to model these kind of tasks on the cloud and in between the cloud and the application, the individual applications. So this is a very high-level explanation of why optimization should be used in cloud computing. So this is some background of AI. Of course, I don't need to say too much. Everybody have felt that already. We are living in the new era of AI. So AI is changing us. So we have so many AI-generated contents, okay, Facebook and whatever. So we use a lot of AI products now every day. So there's no need to this. But one thing I want to say is, in the era of AI, a particular difficulty for us, or a particular bottleneck is for us, is actually we are lacking of computing facilities. Okay, so I give you the graph. You see, on the x-axis is the time. Okay, from 2011 to 2022, and you see that the y-axis is talking about how much computing facilities we need. You see, basically, the CPU performance doubles every 18 months. This is what we call the Moore's law. Okay, but the Moore's law has been over since since at least 2016. You see, let me see how to understand this. Okay, so this is okay, it's not finished yet. Yeah, you see, this is the computation. This is the GPU, I guess. Yeah, for every 10 months, so you see it's increasing from here to there. So the slope is quite flat actually. And then this is the GPU and the CPUs, increasement on the market. This is all we have. Okay, technically, actually, we can exactly calculate how many floating point operations we can do for each second on the market. We can calculate how many CPUs we have produced on the market, and how many GPU, how many CPU. So we can calculate them formally. We can calculate exactly how many floating point operations can be calculated by all the CPU and GPU on the market. So this is basically this is how the GPU and the CPU facilities are increased in the past 10 years, 12 years. Okay, but you will see actually. You see there are many letters. This is the specific company's name. For example, this is OpenAI. Okay, so this means how much computation each company needs in the market. You see, there's a huge gap between the resource available in the market and the facilities the companies need. So there's a lot of needs to increase the computation facilities. So to give you more ideas, this is, everybody's talking about deep learning. Everybody's talking about the large language model, LLM. So you see, I give you some numbers. You see, for example, in the ChatGPT-4, so there are 1.76 trillion parameters for one training. Okay, you have so many parameters to train. And if you put them in the GPU, you need so much GPU resources. Okay, to just store the parameters, no computation at all. Just to put the parameters in the computer. To kick off the training, you need this kind of things to do. Okay, and one NVIDIA, okay, B200 actually only has 192 GB. So basically, you need almost 20 B200 GB NVIDIA chips to store the parameters for one ChatGPT-4 training. Okay, so this means we need so much GPU. We need the facility of computation to do the cloud computing AI. And that's something applied mathematicians can help. That's something I'm trying to help the industry to do this. Okay, I'm helping Huawei to design some AI chips actually at this moment to see how to do that. Okay, so this means yes, the different NVIDIA GPU memory. You can see so far the best one is H100. Actually, we can have 80 GB for each chip. But in China, the problem is we cannot buy NVIDIA chip anymore. So China need to design the GPU by ourselves. Okay, so that's the background. Very short introduction about the AI and the cloud computing. So now let me give you some mathematical problems to see how we can do this kind of things mathematically. So I can promise you all of these applications are real applications in industry. And I can also promise you, I don't know answers to any of these questions. So another thing I can promise to you is that whenever you know how to solve these questions very well, basically you can become very rich. Industry will pay whatever you want to solve these kind of problems. So these kind of questions are very, very challenging, as you can see from my slides. So basically, at this moment, we don't know the exact solution. So, but we have to know some computational solution, numerical solution to do this. Okay. Let me give you the first example. It's the so-called virtual machine scheduling problems. Nowadays some people are not using the physical machines. We don't need to use the machine physically. Actually, we can use the so-called virtual machine. We just place an order on the internet to tell some cloud providers to say, I want to have a machine and with the specific GPU and the CPU and the memory, kind of this. So the cloud provider will do the computation for you on the cloud and then send the result to you through the internet. So this is what we call the virtual machine. But of course, the computation task must be performed physically in some server, but just in the pool of servers on the cloud. So for the cloud provider, the question is, okay, how can I place appropriately a sequence of requests from different customers from different regions and put them very reasonably in the servers and compute this and do this computation very economically and send it back to the result to the back. So everything should be optimized in order to save the cost. So we want to minimize the number of servers that are really used. Yesterday, 2 days ago, I was talking to somebody here, and I mentioned actually, for example, in Huawei's computation, maybe the cloud computation is happening actually not in Shanghai or Beijing. Maybe it's happening in Guizhou or in Inner Mongolia, some other places. Okay, but then they send the result back to Hong Kong, Shanghai, and Beijing, the big cities. And so this is the idea of the cloud computing. So anyways, a virtual machine allows multiple operating systems to run simultaneously on the same hardware device, and each VM operates as an independent system, equipped with the CPU, RAM, and the storage, and so on and so forth. So the VM scheduling challenge is, okay, the purpose of the virtual machine scheduling is to map each VM to a specific physical server to maximize the profit or minimize the resource fragmentation, okay? So to minimize the cost in general. So the static VM scheduling can be viewed as a multi-dimensional bin packing problem. The bin packing is a very classic operational research model. I'm going to show you. Everybody have done this whenever you took any course of operational research. So I'm going to show you why we can consider this problem as a generalization of the bin packing. So the bin packing problem is like this. Before that, I see that, okay, this is the model. So we have different types of machines, VM1, VM2, VM3. So basically, each provider, cloud computing provider, offers several different types of VM. So you can see the parameters is like this. First of all, the number of resource types, okay, 1, 2, 3, for example, here. And I is the set of VMs. D is the set of physical servers. So as I said, eventually the computation must happen in some physical server, okay? And then we have some demand of the IS VM for the n types of resource. And we have the CJM, the supply of the just physical server for the M's type of resources. So the decision variables is very simple. We only have this set of variables. First of all, we have so many servers. We have the J. J means, okay, here where it is. Okay, anyway, we have J servers physically. And then we have to make the decision to see which server will be used for the computation for my customers. So the decision is only binary, 0 or 1. If it's 1, I mean this server must be open to be used. Otherwise, it's closed. Okay? And Xij means, okay, I have to decide the I's job will be assigned to the J server or not. If it is, then it's 1. Otherwise, it's 0. Simple decision variables to understand, right? We have to decide which server will be used and which job will be placed into which server. That's the only decision you have to make. Okay, so the model is quite simple. We actually minimize the number of active physical servers. We want to minimize this. We don't want to open too many servers. Otherwise, it costs money, costs electricity, costs human power, whatever. Okay, and then we have some. Of course, we have some constraints. For example, each server has some physical constraints, physical capacity. So we cannot put too many computations in one server, okay? And then we have some demand constraints. That means all the constraints. So they must be at least one server to serve for one job. So each job must be finished by some server, okay? And then this is binary. So the J server will open or not, and the I's job will be put in the J job server or not. So this is a integer programming model, binary, okay? But of course, you can imagine very easily why it's difficult, okay? Why it's very difficult to solve. Let me compare with you. You know the classic bean packing problem. You have heard about this, the classic bean packing problem. This is very standard, and like we want to have, we have some box. We have some, okay, box. And then we want to put the items in the bin. We have to pack. We want to pack the items in the bin. So how to minimize the number of bin to pack all the items on hand? So that's the so-called bin packing problem. It's integer program as well, okay? And it's NP hard, by the way, because of the 0 and 1. And the volume of the items is known in advance. I mean, for the classical bin packing. For example, in the airport, you want to put all items into the aircraft. Then you know what the items you are going to pack, and what's the bin, what's the aircraft you have. Okay, you want to accommodate this kind of items, and the quantity of items is fixed. That's the classical bin packing problem. But for this virtual machine scheduling problem, as I said, it's very similar as the bin packing problem. At least, I mean, the logic, the philosophy is quite similar. It's also integer programming. It's NP hard, of course. And you can imagine the additional difficulties for the virtual machine problems. First of all, the virtual machine requests the active one by one or batch by batch. And also, the allocated virtual machine may be retracted by the customer. I mean, the request can be deleted if you place an order on the internet. And then after a few seconds, you can withdraw your request. So the arrival sequence is quite uncertain. And you cannot control, right? Customers have the freedom to cancel their order, right? Even you order some food, you can also cancel it, right? You order a taxi, you can cancel it. And one more thing is the additional practical application constraints. For example, under the robust control, some virtual machine cannot be allocated to the same server. This is some additional different constraints. If we are talking about the classical bin packing, the bin is bin. So you can put whatever you want there. But now the bin is a server. So we have some physical constraints. Or we have, for some safety purpose, maybe purposively we don't want to put two things together in one server. We have this kind of additional constraints there. And also, of course, the problem is extremely large. You know, we have millions of customers, and their arrival sequence could be not just uncertain, but also very large, in a very large scale. Okay, so maybe within a few seconds, you'll receive hundreds and thousands of requests. So this kind of questions is much, much more challenging than the classical beam packing problem. And also the response time, so you have to respond to the customers very quickly. In the classical beam packing problem, maybe you can have 1 day, 1 week to, to solve this problem, and then you give the solution to a customer. It's okay. At least a few hours it should be okay. But for this, you cannot put the computation in a few hours. If you buy the virtual machine from some provider, and you place the order, and you wait for the solution, and basically you are not patient enough to wait for a few minutes. Okay, I'm going to show you some other applications. The response time is even more restrictive. Okay, anyways, I just give you some idea of how difficult the problem is. And so, as I said, I have no idea about the solution. I don't know how to solve this problem. And we consult many people, not just myself. I work with the industry people, and we consult many top scholars in the world. And nobody have heard about this problem in papers. Nobody have studied these problems in the literature. No literature at all. Okay? But this is the real application. We have to solve this. Some of my colleagues have been working on this for a few years, and we are providing services. So it's not an excuse that you have no paper to read. This is not an excuse. Okay, you have to give the answers to the customers, right? You cannot say, oh, I have no idea because there's no paper discussing about this. No, this is not an excuse. Okay, give a solution, give a approximate solution at least, okay, to the customer, and then you can help them. You can make more money from the market. So this is the first application. The second application is even more interesting. I'm quite dedicated to these applications in a few years. Okay, during the pandemic, we had nothing else to do, so we stay at home, and we had a lot of time. Okay, we don't need to travel, so we work on this a lot. And then so there's the so-called the live streaming, the video deliver service. So people create videos, and some other people watch videos. And then economics happens, and then money can be made between this. Okay, so the content creator actually are very keen in delivering their videos to more people, and some other people, are very keen in watching some interesting videos. Okay, so in between, the provider of the cloud are doing the business in allocating the viewer, the watcher, to some server, so that the creators can be connected. Okay, so the provider just to do the business like this. We want to schedule, we want to make the connection between the creator and the viewers, okay, and of course optimally. So hopefully we can make this connection better. Okay, so the real-time digital media transmission via the internet, enabling simultaneous viewing of videos, audios, and multimedia content. As I said, because of the pandemic, all of a sudden, this business was just served in a few weeks. So people had to stay at home at that time, or the people, and then you need some videos, you need some entertainment, okay, at home, and the people began to look at it. And then I got this task. So they help us to do this better. Okay, this is an industry problem. Of course, I did that at home as well. Okay, through the cloud computing. So video entertainment, online education, social media, online meeting. So we always do this, right? So the benefit is okay. First of all, person likes to maybe some people like sharing. Okay, on the internet, and there are some business promotion as well. This is a new way of business. Some people became millionaires, billionaires just because of this. Okay, this is what we call influencers, Wang Feng, right, in Chinese. So people like to do this, and it seems their job is very easy. So just stand in a video and give some talks and make some jokes, and you make money. People will give you money about this. But anyway, so behind of this, what's the mathematical problem? How mathematicians can help them to do this? Okay. Well, first of all, if you are watching some video, first of all, you hope the video should be delivered very smoothly. All right? You don't want to see some stops between the videos. You want to say, okay, it's running very smoothly. So this is what we call the quality of service. QoS, quality of service. So the quality of service must be very good. Well, second one, do you have any idea what the cost behind of this business? If I want to make you to be connected with some creator through some servers, I have different choices. I can put you in the server of Beijing, and then the creator may be in Shanghai, so I can connect you. Or another is I can connect you to another server, which is in Tianjin, not in Beijing, and then you can also be connected to the creator. So different connection, different paths will cost differently. So how to find the optimal connection among millions and millions of watchers, viewers, with thousands and thousands of creators? Yeah, not very much about the optimal transport in the sense of PDE, not about much about this. Yeah, it's about I'm going to show you. It's about again optimization problem to do that. Yeah, so you see, this is what we call the bandwidth allocation problem. You know, the major operational cost of this business is the cost of the bandwidth, because all the providers must buy the bandwidth from the telecommunication company. Okay, so all of these are our customers, the big companies. Yeah, if you are using TikTok, Douyin is the Chinese version of TikTok. TikTok's English version of Douyin. Okay. The Bilibili and the Taobao, and all of these are major video delivers in the market. Okay, so you can see, to give you again for MBA students. Okay, I also this monetary measurements to encourage the student to study business. Anyway, so you see, for even just in the Chinese market, you see, as of June of last year, there are 765 million users in China, accounting for 71% of total internet population. A few weeks ago, I was giving the same talk in another university, and some people from Switzerland were sitting there. So I asked one of them, so how many population in Switzerland? It's 7 million, okay? But we have more than 7 million, live stream users here in China, okay? So we have 700 million, 7 million. And then, so the market size of China's live streaming industry will be, you see, it actually exceeds 200 billion RMB last year already. That's a huge market. Okay. So the math problem is like this. Now let's look at the math problem. We have audience, we have streamers or the creators. So as I said, we have different levels of cloud servers. So we want to make the best connection or the, at least some better connection from one streamer to one audience. Okay. Of course, the system is extremely complicated. You can, roughly speaking, you can consider this as a graph, for example, right? So this is a node, this is connection, and a selected connection. Roughly speaking, you can consider this as a graph. But one very serious difference from the graph is actually the law is not conserved. The flow is not conserved. You don't have the conservation law anymore, the flow. You see, in general, when we start a graph, all the flow come into the node will be the same as the flow come out of the flow, right? But for this, it's not true anymore. You know the reason? Because all the flows are data, okay? And the data can be copied. But this is what replicated. So the data coming out of the node might not be the same as the flow coming into the node. So we don't have the flow, we don't have the conservation anymore. Okay, so that's one very significant difference from the general flow graph. Okay. So the like if we're learning the linear programming, there are some maximum flow cuts, cut kind of the theorems. This cannot be used anymore. Anyway, so you see one particular stage to do the bandwidth allocation problems like this. We have the client, so we have the cloud edge. Cloud edge means the last level of the cloud that you have to make connection with the server and the customers. Okay. So we have the client groups and we have the data centers. We have to make the connection. You see, so the clients access the cloud services with direct connections to the cloud edge. As I mentioned, the cloud edge means the last stage of the cloud that you have to connect to the audience. Okay, so the formal representation of the network actually is kind of graph. Okay, by-party graph, and the data set and the client cloud connect only if the communication latency between them meets acceptable threshold. You see, this is the how much time you can have to solve the problem. You have to respond to the customers less than 400 milliseconds. 400 milliseconds means 0.04 seconds, less than 1 second. You have to respond to the customers. And how can you do that? So I don't care which algorithm you use. You have to give the answer, okay, within this time. That's the rule. Okay? Otherwise, you're going to lose the customer. Okay? So, and also you see the data center, okay, in the client groups and the building cycle will give us a lot of new difficulties. Let me see. Of course, it's very easy to understand. We have many customers, we have many servers, so the dimension is very high in the model. And also, in particular, I'm going to explain to you. Maybe this is something new for you. You know, this building cycle, the building scheme. I mentioned, the major cost is the operational cost, is the bandwidth cost. And the provider, like Huawei, Alibaba, they all have to buy the bandwidth from the telecommunication company, China Mobile, for example. And then there's something new for you. In the industry, the telecommunication companies, they charge the providers, the cloud computing providers, by the so-called 95th percentile building scheme. This is something new. I'm going to show you in the next slide. But this scheme gives us a lot of troubles mathematically, because this scheme makes the objective function highly non-convex. Okay? So the model becomes very, very difficult. So let me show you what is the 95 percentile building system. A scheme is like this. So you see the telecommunication company charge the bandwidth cost, not as a constant, but also use this kind of scheme. For every 5 minutes, there will be some floor, there will be some number of floors, right? So they just count the highest one for each 5 minutes, the peak time. So each month we have 89, 28 intervals every 5 minutes, okay? And then they put them in an order, in a descending order like this. Each number means some peak time in some 5 minutes interval. So we have 89 and 28, kind of these numbers for 1 month. And the scheme is like, okay, the very first 5% are totally free. The charging price is going to be here, right after the top 5%. So your strategy, our strategy is, okay, I want to try to make the connection, the scheduling problem, as better as that most of the connection will happen within the first, the top 5 intervals. That's the strategy. Because the top 5% are free. Only the charging price is here. So you have to make as much as possible here within the top 5%. So this is so the objective function becomes highly non-convex, non-linear, and even discontinuous. Okay, so that's some difficulties we have to face. Anyway, I skip a lot of details, and you can see this is the model. You don't like the notation, I know. And then just look at the red words. You say, first of all, we want to minimize the total cost. And the total cost comes from the 95 percentile building scheme. So it's going to be a non-convex, non-linear. Okay. And then we have the demand constraints, we have the capacity constraints, very easy to understand, right? And then we have some other sign constraints. Okay. So this is the model. So let me give you the model like this, and then you can see the problem can be formulated as a mixed integer programming problem. So you see, first of all, again, the objective is, okay, the total build bandwidth usage under the 95th percentile building scheme. So within one interval, actually, we have to solve this problem. Within 1 5-minute interval, we have to solve this problem. Okay? So, and then the first constraint is the bandwidth usage is bounded by the capacity. And then second is the demand constraints. And then this means the top 5 time slot of array. So we use this to explain this. So whether the time slot from t to t plus 1 is a free slot for the center, the data center, then if it is, then we call it 1, otherwise it's 0. So anyway, you can say you skip the specific meaning just mathematically. If you look at the model, you'll see, first of all, again, it's bilinear programming, integer programming problems. And there are some constants and some linear function, linear objective function. So except for this kind of constants, the model seems okay. I mean, it's linear, but it's not but there are some integer constants. Okay. So let me look at the second stage is let me do this quickly. Yeah, this is the overall model. So you see the second stage is actually a large-scale linear program model. So if we do, so I have to go back in here again. So this problem can be formed as an mixed integer programming. So some variables are integers, sometimes are not, are continuous. So basically, how to solve this kind of problem? We have many these kind of problems, mixed integer programming. So our idea is actually we do a 2-stage framework. And we use some operator splitting. The idea comes from PD, actually, from some mathematicians in last century, in 1980s, 90s. Okay, we use operator splitting to split the continuous variables and the integer variables. First of all, we split the operator, and we handle this integer and the continuous variables separately, individually. So for the first stage, we design some algorithms. So this is some algorithm we design to determine the integer variables. We have to find out the integer variables first of all. And then the problem transitions to linear programming. Okay, so we have millions of decision variables. All right, so the second stage is purely a linear programming. We have to solve this kind of linear programming. Okay, but the problem is the dimension is really high. Okay, so you can imagine actually dimension is in this level. We have so many billions of variables to solve. Okay, so we cannot use any commercial solvers, Citrix, Groupy, we cannot use this. We have to design our own algorithms to solve this. Right. So this is a typical integer programming. Okay, and so let me give you the comparison between the classical assignment problem and the bandwidth allocation problem in live streaming. You see, the assignment problem is another very classic operational research problem. We have n persons, we have n jobs, and we want to assign each job to each person. So, but we know that cost for each person to do any job. So we want to minimize the cost by assigning all the jobs to other people. So, but each job should be done by only one person, and each person has to do one job. So this is the classical assignment problem. You say, okay, so we have the variables xij to make the decision. So xij means the ith job will be assigned to the jth person. So it's 0 or 1, right? So this means each job can be done only by one person. And this means each person has to do one job. And this is the cost, right? So we want to minimize the cost. And then this is the classical assignment problem. So similarly, we have another very similar problem in live streaming and the last stage when we want to assign each audience to some age clock. We do have the similar things, right? We assign a viewer audience to the server. Okay, you see, this is the bandwidth allocation model in the live streaming. So similar, okay? But the problem is, okay, first of all, it's also mixed integer programming. And the model includes millions of variables. The dimension is very high. Okay. So, for example, our products actually are serving for 15 million users. Okay, and so this is the size of the numbers of the users. Okay, so it's millions of variables. This gives some difficulties to solve, right? So, and also even though we tackle the problem by separating the integer and the continuous variables, it requires not only an efficient method to determine the integer variables, but also an efficient approach for solving the large-scale linear programming problem. So we have to know how to solve these kind of problems. So let me give you some mathematical steps here. So we all know the set of point problem. We're going to minimise and maximize two functions simultaneously. But these two functions, these two variables are coupled by a bilinear term. So this is a very standard, convex set of point problem. Okay, theta 1, theta 2 are both convex. A is matrix. So let me give you some very interesting idea of how to solve the large-scale linear program by the set of point problem. I'm going to show you. This is the most mathematical part we made for today. You see, for example, we have linear program. Okay, with inequality, equality, and interval constant. And then, of course, we know we find the set of points. We have the minimax model for the set of points of this. Is that right? Okay. So the large-scale linear program in bandwidth allocation problem can also be formulated as this kind of by this. I mean, this is just an illustration example, but similar. The very complicated models in live streaming can be also done similarly. Let me use this as an example to illustrate my idea. So we have the linear constants and we have the set of points. Okay. So we have the so-called trompe-l'oeil plot algorithm. If you are working on image, you know this kind of algorithm. So the idea is very simple. We just split, x and y separately. We do x first by fixing y, and then we solve y by fixing x. Gauss-Seidel idea. And of course, a slight difference here. We do the extra step here. Okay. So this is what we call the trompe-l'oeil plot algorithms, which is very, very useful in image processing and computer vision. And of course, we proved them. There's no convergence in the paper. Okay, the convergence was not proved, and we proved that the convergence for alpha equal 1. When alpha equal 1, it's very easy to prove the convergence. So this is so far this is the most popular one in this literature. So anyway, let's focus on this. Okay, there are not a long story to explain how to do that, but I skip them. Anyway, so let's focus on this case. So we can do this together. So you see, this is set of point. This is a CP algorithm. And the convergence condition, mathematicians always like convergence condition. So the convergence can be guaranteed whenever these two step sizes are bounded by ADA. Okay? And this is, and also we can relax it. I mean, for the geometrical case, this is the optimal solution. This is something we have done because we hope R and S can be smaller. Can be smaller. So the better, the smaller. You know why? Because RS are basically the step size. So we don't hope RS should be large enough to large. Otherwise, the convergence is very slow. You see, when R is large and it's very close to K, you cannot move forward. Okay, so R and S should be larger. So, but we prove this is the best condition. You cannot be better in general case. Okay. So anyway, so this is some CP algorithm, CPHY algorithm. So let me show you how to solve this linear program by the CPHY. You see, I just remind you, this is linear programming. This is a set of point reformulation. And if you apply the CP, this is CP. Okay, simply put them in here, and you get this. You get these iterations. Everything is just a closed form. Okay, and the very interesting is that each subproblem is a fully separable box constant concave quadratic problem. So this is something I told you yesterday. So actually, for this, all of the solutions can be solved in parallel. So it's not an acceleration of the mass storage. It's just an acceleration of the implementation. Okay? You apply prime dual to linear programming, you end up with this scheme. Okay? And these schemes are very simple to do. Okay, I think there's some typos. You can skip this. Okay, this is the final result. So anyway, so you see the main information is here. Only one-dimensional optimization problem should be solved because they're separable. So you see, when we solve I obviously use this in my teaching when I was teaching the optimization course for my students. You see, if you minimize fi, x, okay, I may be very large, okay, you have n functions to be minimized. This might be very difficult. But the difference is here. If you want to minimize I from 1 to n, fi, xi. This is the one-dimensional problem, n one-dimensional problem. So this problem could be extremely easy. Okay? So, for example, we all know Lasso, or basis of many different names. You see, this is the one dimension. This is the L1 norm. This is the L2 norm. Okay, this is not smooth. Do you think this problem is difficult? No. This is exactly a subproper case. So this problem has this optimization problem has closed form solution. Okay, but if there's A, when A is not matrix, not identity, this problem could be difficult. It's the same story. So the linear programming, if you apply the setup point reformulation and the CP algorithms, all the problems can be solved in parallel. Very simple to solve. Okay? There's no acceleration at all. Anyway, so you see another idea is, okay, as I mentioned, we want to solve some assignment problem. Assignment problem, basically, this is a binary program. We have integer, x and j. But there's a so-called A is the totally unimodular. This is some terminology from integer programming. I didn't know this before. And my colleague told me, okay, because this matrix, which is writing here, this is A, the matrix actually can be proved as a total unimodular. So we can relax the 0, 1, the binary constants to an interval constant, and they are equivalent. This is not by accident. So the story is like this. We want to try to solve this model, and then we did some numerical experiments. By relax them to the continuous case. And we found the solution are always the same, very, very correct. So I didn't know why. So I came to my colleague's office. He's an expert in this program. So okay, why this happens? So yeah, this is not by accident. It's a must because A is total unimodular. So I'm happy. Anyway, so you see the classical assignment problem can be relaxed to the linear program problems. So let me give you some very interesting story when I help the industry to solve the problem. So you see, this is matrix A, and this is AAT. If you remember when we apply these algorithms, the condition is we have to control the stepsets by AAT, the norm. For this matrix, AAT matrix is like this, very structured, okay, but a huge matrix. And at the first glance, you have no idea why how we can handle this matrix. But when you calculate the rho, the maximum eigenvalue, rho ATA equivalent to rho AAT equal to 2n. So AAT is large, where n is large. So if we go back to the algorithm, you see the CP algorithm. That's the CP algorithm. So you see, when AAT is 2n, then this number is too large. This number is also too large. 0.75 doesn't help too much. Okay, when AAT is large. And image A is 1,000, for example. If A is 1,000, then the right-hand side, the bound is 2,000. Then the step size should be very, very tiny, and you cannot move forward, basically by iterations. Okay, and even this optimal condition cannot help you too much. This is what we call the rigorous of math. So sometimes mathematicians are too rigorous. We just, we like the rigors in math. And sometimes we are constrained by this rigor. So we don't know how to move forward, how to relax these conditions. I told you, I emphasized that this is the condition for the CP algorithm. And this is the best, also this proved by us. This is the best of optimal condition for the step size. And when AAT is large, either of them is useless. is useful. Either of them can help you too much when AAT is large. So when AAT is large, for example, for the assignment problem, how can we do that? Okay? So we got a very, very interesting idea. So let me show you. So AAT is to n, so n is large. But we observe actually the trace of AAT or ATA is 2n squared. And we know the average eigenvalue of ATA is constant. Because the average is equivalent to the trace of AAD divided by the maximum eigenvalue of AAD. So no matter how large n is, the average constant, the average of the eigenvalue is 2. It's constant. It's irrelevant to n. For us, that's big news. Then, heuristically, institutions, okay, why don't we just skip about the rigorous? And of course, not completely. But also, we think about why don't we just replace the condition of AAT by the double of average? Which makes sense, right? Average basically means the midpoint of the interval, basically. So if we multiply this average number by 2, which is 4, why don't we just use RS equal 4 as the condition instead of AAT, which is too huge? This is the heuristic. No idea why it's converged. But let me give you the example. So you see, this is some very interesting result. We can accelerate the algorithms by this very simple condition by about 20 times, 30 times. Just simply by this very, very simple heuristic, very simple intuition. So this is this is the dimension of n. This is how large the matrix should be. Okay, like for 1,100. Okay, and this is CPHY algorithm iteration. Just look at the iteration number because the computation per iteration are similar. And this is the so-called the best condition by 0.75. And you can see usually 20% can be saved by this condition, but this is not big news, right? 20% is nothing for industry. And then you see when we use this very simple idea without any math proof, but still it's not coming from nothing. It's just come from the some very well thought idea from the to tackle the difficulty of AAT is too large, right? And then you see immediately the iteration number will be saved by 30 times. That's by the same idea. We use that in industry. We help them to solve this problem. Because when you implement an algorithm, sometimes you have to know how to adjust your strategy. If you have this strategy which doesn't work, if the strategy comes from a paper, it's published, it's proved, it's very well written, it's probably a very famous algorithm, whatever. But then when you implement the algorithm, you have to adjust. For example, this is a very good example for us to see how can we do in industry for some real life applications. If you stick to the theory, then you can end up with this. But if you relax a little bit of the condition, you accelerate the algorithm easily by 30 times. 30 times. And we don't know the theory, but that's just because we don't know. It doesn't mean there are no theory. It's still, we need to find the theory behind, right? You can only say we have no idea about the theory yet. Okay, but something may be there that we don't know. Anyway, so this is an example to show you how can we accelerate them. So we use a lot of different algorithms in the system. So you see, this is some evidence of how we help the industry for this live streaming business. We saved money for the industry for about 108 million US dollars in 3 years, simply by some optimization algorithms. Okay, and we helped Huawei to increase the number of users by 10 times in 3 years. Then we are serving, as I said, we are serving 15 million users in more than 60 countries. Okay, and many of the problems behind are solved by the algorithm I just mentioned. Okay, so this is some research work we got from with Huawei together. So maybe one more application for you is like the so-called the post-training pruning for large-scale language model. This is a new application, very new application from the large language model, okay, LLM. So you see the neural network, I was talking about neural network, but neural network is talking about neuron in the brain, okay? We try to learn biologically how the brain works, and then we try to make the same philosophy in the computer. Okay, this is neural network. So you see, well, this is how the neurons are connected in our brain. The neurons are connected in the brain at the birth. It's like this. It's very sparse. There are not too many connections between different neurons. Okay, and that's why we didn't know too much when we were just given the birth. We couldn't speak, we couldn't learn, couldn't sing, we couldn't walk, right? Just because the connection, the neuron are too sparse. And you will see, actually, after 6 years later, basically, the connection is much more dense. Again, you have different neurons, different functions can be organized by the brain. So there are much more connections in different neurons. And very interestingly, so biologists actually observe after a few years more, for example, in the teenage, the 14 years old, the connection becomes sparse again. There's some real pictures, okay? So that means actually, this is the process of training. You train, we learn a lot, your parents will teach you, maybe your classmates will teach you, and you learn a lot you receive a lot of information. And this is the process of training. So you build up the connections from different samples, different numbers, different data. And then after a few years more, the brain decides to delete some connections because the connections are useless. Or we can represent the knowledge by a sparser network. So this is some real pictures from the brain, human. You see the connections are sparse again. So we want to use this to the large language model training as well. So 3 minutes? No, 1 hour, right? Oh yeah, okay. So anyway, I'll finish this story for you. So the pruning is means you want to cut off some connections. Okay, after you finish the training, then finally you want to represent the networks by less connections. This is what we call the pruning. Just like you cut off prune the tree, for example. Okay, so this decision should be made by the large language model labs. So I don't have too much time to explain to you, but anyway, so you can say the pruning is, first of all, the very first pruning is like, I don't care the structure, just pruning. I just cut off some connections. But some other one, which is used by NVIDIA, is what we call the 2 and 4 semi-structured pruning. That means for each row, I only, for each row, I remove, let me see how to say this. Okay, for each square, for example, for each square of 4, I cut off 2. Okay, this is the structure. This is NVIDIA's architecture. We have to do this. So we end up the model. To do that, we end up a model like this. So because of the time, I end up this model. So whenever you learn optimization, you know this model. This is Lasso model. This is exactly the model here. Okay. So X slide. So okay, here's okay. This is a variable. This is a variable. This is the input of the last layer of the network. Okay, and we hope they should be the same after the pruning. Should be the same of the result without the pruning. So they should be the same. And we hope they have some sparse structure. So we use L1. We try different terms. We try different. For example, the regularizer. Try different one. But turns out actually the simplest one is the best. So we just use the Lasso model to do the pruning. Okay, and I can show you. We can use FISTA. Very simple, very famous algorithms for solving the Lasso model. And we just use this. The simplest one works the best. So we use this to do the pruning. So far we are helping the industry to do this. So I don't have time, so I just skip some other things. Maybe one thing, I just use 1 minute to help you, to explain to you. So how to simulate the hair of a digital human being is very important in industry. Okay, so we want to simulate how the hair move should be. So that's a very interesting problem. And it turns out actually the model is highly non-convex, and it's highly but the idea is each human usually has 120,000 strands of hair, and each hair should be split as a 200 or 100 this elastic rope. And then we have to simulate the physics. So it turns out we have to solve a non-convex optimization problem with millions of variables to simulate the hair. That's very useful in, like, for example, in movie industry, in the online game industry, and in digital fashion industry. A lot of this should be solved by mathematicians, especially by PDE guys, and OD guys to do this. So yeah, this is NVIDIA's product. This is NVIDIA's product on the last year. So they use ADMM. They use the Docker structure for splitting. If you know this algorithm in PDE, they use this kind of algorithm to do this. Okay. And they announced this product, and my colleague forwarded it to me. And then we look at the paper and found actually from optimization point of view, we can do something better. Yeah, thank you. So you see, this is the simulation of how the hair can move. Okay, but of course there are a lot of GPU parallel computing by NVIDIA. So, but I told you already, so basically they use the Docker structure for the operator splitting algorithm to do this. And if you look into the model, you'll find the model is convex, but it's highly structured. So how to take advantage of the structure of the model so that we can design some better algorithm to solve this. This is something we are doing, okay? And we made some progress towards the solution of this. So it's very interesting problem. I don't have more time to explain some optimal control problem in PDE. So thank you very much for listening.
Very central, where we are tackling the problem, Xiaoming Yuan. Just have some very often spot that the most challenging problem presented, for example, last year is the multi-dimensional practice program.
Yeah.
Now very well structured, right? So maybe there is some reason to learn because we don't know the distribution of the stone, but we know the solution just over there once that they can given. Okay, and maybe very well structured, but this kind of structure we don't know.
Yeah.
But maybe machine learning can help.
Yeah.
So if you
Yeah.
from
Yeah.
just learn some kind of way, but some kind of different network, and to predict roughly
Yeah.
and help us to overcome
Yes, this is a very meaningful suggestion. Actually, we did this all the time. I didn't mention that, but as mentioned, the response time of the request is very short, like 400 milliseconds, like this. So it's not possible to provide the real solution, the real-time solution. So we did a lot of training offline. Offline means we collect all the data. So we are learning this structure of the data all the time. And once we receive the real request, we actually use the outputs of the training process from the scratch. And then we start from the output of the offline training result, and we solve that. So all the structure, all the favorable structures actually are used already. Although we don't know what the structure is, we cannot it's not visible, but it's already hidden in the solution. So we use that. Yeah, we are doing machine learning all the time. Yeah, for this. Otherwise, it's not possible. Yeah. Yeah, it's more than warm start. You know, when we do optimization, right? We have the so-called warm start. Means you don't start from random. You start from some well-knowledge, informed solutions. But it's more than that. You know, as you mentioned, we learn the structure. We train the data because we keep the historical data together. I give you an idea. You know how large the data is. You know, for 1 month data, 1 month collection of the data, we have to solve an integer program with 120 billion variables, billion, not million, variables to do that. It's not even to get some feasible solution, not talking about optimal solution. So that's the real application. That's the real data set. So it's much more challenging than some regular problems. Yes, meaningful. Yeah, very meaningful. Yeah. Yeah. Have to catch up to other parts. Yeah.
Speaker.
Thank you.